Hey, good afternoon, everyone.
Afternoon.
So, welcome to week 7. So, we're coming up on the 2/3 point of the quarter. We basically have 4 weeks left, which is shockingly fast.
It's been too much fun.
Hopefully, it has been fun. I know it's a lot of work. This course is probably the toughest in terms of learning material and how much there is to take in, and how many new concepts for most students. So it's definitely a super challenging course like that. But on the other side of it, I think most people find sort of a much better programming experience, a more solid understanding. Maybe not right away, but eventually, building on this. Some people think 250 was by far the hardest. Yeah, 250 is a lot of work too. I guess all the courses are a lot of work. Um, but it's good stuff. No traffic lights in this course though, so bonus there. Um, and no state. Well, no, we do some state machines. Anyway, my plan for the remaining 4 weeks is to, today I want to talk about PA3. I want to introduce PA4, which has been up for a few days now on Canvas. So I'm talk about PA4 and then continue talking about binary search trees, which is the subject of PA4. And we'll get through most of that today. And then Thursday we'll probably finish up, our first pass over binary trees, including talking about perhaps balancing trees. And then next week we'll probably talk about dynamic programming, which is related to recursion, and it's a sort of essential concept for speeding up recursion. And then we'll spend a week probably talking about searches and sorts and go through a bunch of different sort algorithms. And we'll definitely come back and talk about tries, which are extremely wide trees. Binary trees have 2 children. Tries have 20 or 30 children, maybe 100 or 200 children on each node. So they're very different. And that will
I
probably take us through the whole course, and we'll do a little bit of wrap up the last class probably. Yeah, go ahead.
I have to ask a question here because I've asked a few engineers I know over the last few days to see what their opinion on this is, but I kind of got back a vague answer. Why, in particular, are we trying to use recursion here versus loops? What I've been hearing is that recursion is less susceptible to immutable variables or something like that, but it didn't quite make sense to me.
Huh. Um, we're going to talk about a lot of specific algorithms for manipulating trees today, and most of those algorithms that we talk about will be recursive. And as we go through those, we can be thinking about how would we do this without recursion? What would it look like to use a loop? And I think as we go through those, you'll start to see answers to that question. Because the recursive code will usually be, 2, 3, 4 lines of C. And it will be very clean because we'll be thinking of recursive algorithms. And if we back up and we try to think about how we would do something non-recursively, in the case of trees, it's almost always going to be a lot more complex and a lot more confusing. And so the main reason we're doing recursion with trees is because it's a lot simpler. Other than the challenge of getting our brains to accept recursive algorithms and such, the code is just a lot simpler, and the algorithms really kind of lend themselves to recursion. And so we'll do a lot of examples of that, and I think that will at least partially address your question. If not, definitely come back and ask it again. But I think you'll see some examples of that. You also said in chat you had some questions about balancing, and we're not going to be balancing trees for PA4, but we are going to talk about tree balancing probably either on Thursday or next Tuesday. What we will talk about tree free because that is part of PA4.
Yeah, so far I've gotten the initializer to work recursively, but I keep running into this interesting problem with my recursive tree free where it's always a leaf node that for some reason isn't treated as null after I free it. I feel like we'll probably talk about it though.
Yeah, so tree free is a good example of a recursive algorithm, because how do you free a tree? Free the left subtree, free the right subtree, free the root. That's it, 3 steps. You don't have to move through the tree, you don't have to keep track of where you are and come back and move in a different direction and so on and so forth. Just free the left and right children and free the root.
I got to that point, but like I would get all the way down to the bottom leaf node. I'd free it, and then I'd come back to its parent. And before I could, once I had freed a node's 2 child nodes, and they were both considered null, I would free that node and move on to the next node.
How do you move on to the next node? How would you move on to the next node?
So it would be an LNR traversal. So I start from the root node, and if both of its children are not null, it's going to call tree free on its left child, and then it keeps going and going until it gets to the left bottom one.
So tell me what you mean by it keeps going and going. You talking about your code, or are you talking about the CPU?
The recursion keeps recurring until we get to the bottom leftmost leaf node.
Okay, good.
And then both of its children would be null, right? And then I would free that node and move back up to its parent, and then try to free its right child if both of its children are null. I would move back up to the parent, and since both of its children are now null, I remove that node.
Okay.
And then I move back up to its parent, and I go to its right child, and so on and so forth. Right?
Yeah.
I think that's the left node, right node algorithm, right? I keep running into this situation, though, where it happens at the leaf node level, where I'll have freed both of the root nodes, or the leaf nodes, and the parent node to the leaf nodes, for some reason, it sees the freed nodes as not null. It cannot read those characters, but it sees them as not null, and therefore I can't free it because it doesn't look like both of its children are null.
But you've already freed the children. Why are you looking at the children again?
Well, if they're both null, I know to free the parent, right?
So let's put some. So we're gonna have to go over this today anyway. So we may as well do this right now, since we're talking about it. Let's talk about how we free a binary search tree. And so there's nodes. And it may not be, a symmetric looking tree, but it's a tree, and we've got access to the root node, right? And so what is this called? Tree free. So let's free the tree whose root is given to us as the argument. And the way to think of this, instead of moving down and finding each node and releasing it, is let's describe the process recursively. Free this, free this, free that, and we're done, right? So we're going to write a 3-line function that's going to use our tree free function to free the left and right subtrees. So we're going to say tree free root arrow left, and then tree free root arrow right, and then just a plain old free on the root, and that's almost all we need, except that the way I've written this, it's going to recurse forever until it segfaults, because this will call tree free on this circled subtree, and when I call tree free on this, first thing it'll do is call tree free on the left subtree. And when I call treefree on this, first thing it'll do is call treefree on this single node. And when I call treefree on that, what it's going to do is call treefree with a null argument. And if I let treefree take a null argument and I say, let's look at null arrow left, that's going to segfault. But if our tree is empty, there's nothing to free anyway, so we need one more statement here. If root equals null, just return. And so there's a completely recursive tree-free algorithm. And it's 4 statements.
I probably overcomplicated it too much because I was like, I would make a temporary node that would be the roots. So I could I could set the root to the root's right node, the root's left node, and then I'd send it back to root when I'm ready to free it. But for some reason, that keeps causing problems. I should probably just try rewriting it this way.
Okay. What are you doing after you set the root equal to temp right?
Okay, so if the root is not null, I would execute an if or an else statement. The if statement is if the root's left and the root's right are both null, then go ahead and free that.
Good.
So like, it's a free root. Else, make a temporary node of the root. Set the root to its left node. Then tree free that root.
Okay.
When you come back, root is going to equal its right node.
Temp's right node?
Free that. Temp's right node.
Okay.
Then come back and then set root to temp and then free root and return.
Okay. That sounds good. When you come back from that first call and you set root equal to temp right, make sure that's not null, right?
Okay, yep.
Because it sounds like you don't want to call this algorithm with null. That should work. There might be something that's just not quite perfect in there. But I mean, that sounds like it should do the same thing. So if you can't find that, yeah, come by and let's look at it in office hours. Because general comment here, right? You should always feel like if your code should work, it should work. And if it doesn't work, don't just say, oh, I guess it's just weird, right? That's a horrible way to think about any subject that you're studying. You know, if you're studying economics and you think you know how to answer a question, but you get the wrong answer and your teacher says, oh no, you should just do it this other way, you'll get the right answer, that should bother you, right? If you're doing a physics problem and you think you know how to set it up and get an answer, but you're getting the wrong answer and your teacher says, oh no, you didn't set it up right, you have to set it up this other way, right? Make sure you understand why the way you set it up is not right. Because if it makes sense to you and it's not getting the right answer, there's something wrong. And you want to correct that up. You don't want random rules like, oh, if there's an inclined plane involved, then I can't use the stuff I know about friction. I got to use this other stuff, right? It should always, you should come away in the end with a consistent understanding, and especially in computer science, unless you're running Windows, if you're doing something that you expect to have a certain result, it should have that result. It should be absolutely predictable. So yeah, that's a good example, and like I say, if you don't find that, let's go through it in office hours.
Yeah, I'll send you an email about it and see if I can come by office hours. It really should feel like it should work to me.
Yeah, and it sounds like it.
Just for the hell of it, after I call the freeze on those nodes, I make sure to set the left and right node to null. For whatever reason, it sees it as non-null after it's gone through the free.
Interesting.
I can't quite understand that. Go ahead.
Once you go through free, you can't look at it. It might be null, it might not be.
You see, that's the thing. I test to see if both children are null before I go ahead and try to free that node.
Okay.
So I don't leave something behind.
Yeah. Sounds interesting. So yeah, here's the tree-free part of a binary search tree package, and this will be part of PA4. We'll talk about PA4 in detail, but this is a nice sort of warm-up example of recursion where We're not looping. We're not, trying to free this by hand. Suppose you were a computer and you wanted to free this tree. Well, you'd need to put, some kind of marker down here at the root and say I'm going to the left, and you'd go to the left and say, okay, well, I need to free that node, but before I free that, I've got to free everything to the left, so I'll put a marker down there. Now I got to free this node, but first I've got to free everything to the left, so you put a marker down there, and you say, okay, here's a node, no children, all right, I'm going to free that. And then you got to come back to that last marker you put down and say, oh yeah, and I've got to free the stuff to the right. Let me put my marker back, free that node, and this could be, a whole tree down here. And when you're done going through all of that, you come back and you say, now I can free that node itself. And now I can go back to that last place that I remembered, which was right here. And, if there's stuff to the right, I need to free all of that. And then come back here and free that node. And now I come back to the first place I remembered, and I say, okay, well, before I can free this, I got to free everything on the right. And you start doing that again, putting down markers and freeing different sides. And when all of that's done, you come back to this and you say, oh yeah, and I can free this, and you remember that's the root, and now you're done. And you end up having to code a stack that you use to keep track of where you are in this process of traversing the tree. And so without recursion, the tree-free algorithm is pretty complex. It's a lot of housekeeping to keep track of. But we're not trying to write an algorithm here that does that. We're completely re-envisioning this problem and saying, how do you free a tree from memory? Well, there's only three pieces to it. There's a left child, a right child, and a root. Let's just free these two using this amazing tree free function that I know about, and then we'll just call, free on the root. And where does this amazing tree free function come from? Well, we just wrote it. Right, using the treefree function.
Can I ask you a quick question
Yeah.
about the function? So, when you use a return statement in recursion, does that just return you from that part of the function back to the last step?
Exactly. So right here, when I call treefree, and some stuff happens when I say return, I'll come back to here. And then in that call to treefree, when I say return, I'll come back to here.
Okay. Gotcha. Okay.
And I can put a return at the bottom, but I don't need it. Yeah, and that's the necessary thing that makes recursion work, is that it remembers where you were, so when you return, you just come back one level. And all of your local variables, like root, are local to that instance of your function call. And so if I call treefree with a new value of root, which is, this subtree over here, inside that execution, this is what root is. But when I return, root will be back to, what it was before I made the call. And that's the other thing that's essential, is that your variables are preserved. And all of that works because, guess what? The CPU is using a stack to preserve all of that information for you. So we are using a stack, we're just not coding it ourselves. It's happening for us in these function calls.
Just went ahead and tried that tree-free algorithm, and it's magic, dude.
Isn't it?
Perfect.
Cool. Nice. All right, and someone asked in chat, how does dynamic programming differ from divide and conquer? Dynamic programming is often used with divide and conquer, but it's an embellishment to other algorithms to speed them up, basically. It's a way to avoid doing needless recursions again and again by basically caching results of function calls. And we'll see a lot of examples for how that works and where it kicks in. Cool. Yeah, it's fun stuff. All right, so let's talk about PA3. So third programming assignment is graded and back with comments. And so PA3 looked really good. We were building a hash table of license plates and first and last names, and then interacting with that through a main program. And by and large, this looked really good. So there were a few things that a lot of people got tripped up on, and then there were a few things that a few people got tripped on. And so what are some of the issues? So Valgrind issues, right, is one of them. If I have, you know, a struct node, I don't know what we want to call it, you know, blah, and I malloc space for it, right? And blah has fields like plate, and blah has fields like next, and so on. You got to remember that every variable you use in a C program needs to be initialized before you can use it. So if you make an integer I and you're going to use I in an if statement, you really want to initialize I first. If you're going to use I on the right hand side of an assignment statement, you need to have assigned I a value first. If you're going to set I equal to, you know, the result of scanf, you don't need to initialize I. It's going to get its value from that function return. But don't ever assume that an integer variable is 0, right? It's a common value, but it may not be. So same thing with pointers, you know, blah arrow plate is a pointer to a character. What should it point to? I don't know. Is it pointing to null? Maybe, but I don't know. So when you create the sentinel node of a list, right, the next field is pointing to the first node in the list. If you want that to be null, make sure you set it to null. And when Valgrind is complaining about things during execution, and it's not talking about memory leaks, but it's saying, you know, conditional jump depends on uninitialized values, it's talking about this. It's talking about cases where, for example, you're saying if blah arrow next equals null, and you've never assigned a value to this. Now, if you set this equal to malloc something, or you set it equal to new node, or something like that, that's fine. But if you never assign a value to this, and you encounter an if statement that uses this, you're going to get an error from Valgrind. And it's saving you from yourself by saying, hey, you haven't given this thing a value. And your code might work because typically we assume these things are null, and malloc tends to give you nulls back, but it's technically an error. So that's the biggest source of Valgrind errors while your program's executing. Memory leaks are in some sense a totally different issue, right? That has to do with mallocing and not freeing. And that's just a question of going through and figuring out, you know, where you allocated memory with malloc and how you call free to release that. I don't think I noticed anybody who forgot to call fclose, but a lot of people discovered if you don't call fclose after you process a file, it registers as a memory leak, because fopen uses malloc to allocate memory, and one of the things that fclose does is it frees that memory that was malloced by fopen. And I probably would not have taken off the full points for that, but I would have said, you know, make sure you call fclose, and so on. And it's good to close out your resources anyway, because sometimes, you know, on some operating systems you can't open the same file from two places, and if you open a file and you don't bother to close it, other people trying to open the file might get, you know, an access error, and so on. I think Windows doesn't do that anymore, but it used to. Alright, so let's see. Segfaults. Don't ever segfault, right? Segfault is throwing your hands up in the air and saying, I give up, right? You don't want your program to do that when your teacher is grading it, or when your customer is reviewing it and getting ready to pay you for the work you did, and so on. Segfaults basically say, you know, something I didn't plan on, something unexpected, something I don't understand is going on. And you don't want that to happen. So if you're trying to get, you know, some part of a program to work and it's segfaulting, my suggestion is take that part out, you know, and put a note with the submission and say, hey, you know, my memory-free program was segfaulting, so I commented it out. And, you know, you'd lose points for a memory leak, but you wouldn't lose points for, you know, your program blowing up every time that you try to exit. So watch out for segfaults. But, you know, your best option is, if you can make them not happen at all, by getting rid of whatever's causing it. That's your ultimate goal. And, Some people added new data to the end of the linked list instead of the beginning. Technically that works, right? If you've got a linked list coming from your hash table and you get a new node and you decide to put it at the end, that works fine, right? We don't require a particular order, but why would you do that? Because the longer your list is, the longer it takes to move all the way down to the end to add a new node. And since we don't care about the order, put your new node in the beginning. It's an order one operation, right? Have your new node point where the sentinel's pointing, have your sentinel point to the new node, 2 steps, and your node's in the list. So that was why the assignment said insert new things at the beginning of the list. The reason we did that for having most recent stores closer to the front. Yeah, just for speed. And if we care about the order, if we wanted to alphabetize or something, then we do like PA1, we move through and find the right spot and so on. But, the linked list is a concession to, the universe is not perfect for us, and we can't have, just one entry per hash table value. And so, multiple things pointing to this element in the hash table, we put them in a linked list. But we try to make this as efficient as possible. We can definitely make the add very efficient by going in the beginning. The search, we just have to eat the performance hit and say, I'm going to search every single node until I find the thing I'm looking for. That's just the cost of doing business with a hash table if there's not enough space. I'm passing first name and last name to the arguments. Why didn't it work to allocate the memory within the function itself? All right, so let's talk about this string business. So allocating space for strings. So here's our node, and it's got a plate, a first, a last, and a next. And when we draw pictures, we would usually just write the value of the plate in here. But remember that these strings in C are pointers. So this is really pointing somewhere in memory where we find a set of characters corresponding to the plate, first name and last name. And so allocate the memory within the function itself. So our list add, if we just think about the linked list package, we say list add and we want to give it, a sentinel node, a plate, a first, and a last. All right, when we call list add, these things should be pointing to locations in memory containing the strings that we want to store. And so inside our list add function, we create a new node, and it's got fields for plate, first, and last name, but these are null to begin with. And so we need to do something like, new equals malloc, and then new arrow plate equals, and we need to set up space so we can copy this argument into here. So we do a malloc based on the length of the thing we want to copy, +1 for the null terminator, and then we do string copy. And string copy, remember, copies character by character up to and including the null terminator, and it copies from this argument to that argument. So it goes into memory at the address given by this, reads a character, sticks it into memory at the address given by this, increments its internal counter to the next location in memory, reads the character from there, copies it into the next location after this, and keeps going up to and including where the thing in memory is a null, character 0. Copies that, and then it's done. So if that's your list add function, your hash add function really just looks like this. So hash add, here's your hash table, here's the plate you want to add, here's the first name, here's the last name. Hash add just calls list add. It says list add, so what's the sentinel node of the list that we want? Well, the sentinel node is stored somewhere in table, And which sentinel node do we want? The one given by our hash function. So take your license plate, run it through the hash function. That gives you an index in your hash table. At that index, I find a sentinel node. And what do I pass to it? The plate I want to add, the first name I want to add, and the last name I want to add. And that's my whole hash add function. It's one line. And the real work is happening, inside the list add function. Make a node, squeeze it into the list, allocate some space, string copy the fields. So this question in chat about passing first name, last name to the pointer arguments for hashFind, why doesn't it work to allocate the memory within the function itself? Or are you talking about allocating it inside the hashFind?
Well, when I wrote it, I spent a lot of time on trying to figure this part out. I'm trying to figure out the names associated to the particular plate, right? And so then I have to be able to save that information inside some variables.
Mm-hmm.
And if I allocate room, if I go inside my list find function, then I allocate some space for those strings to be able to return them. Then when I return them, the pointer doesn't recognize that there's it doesn't recognize that there's space. It's hard to describe.
Yeah, no, I think I know what you're saying. It's the difference between returning characters and returning pointers to characters. So if I have my list find function, so I've got a sentinel node, and I've got a plate, and a first and a last. And I do some stuff in here, and I get to a node that let's call it current. And current is the node that matches the plate, right? So if I were to say something like first equals malloc, and allocate some space, and then string copy into first, and so on, right? This is fine. This is making a chunk of memory, and then it's copying, the name from the node in the linked list into that block of memory. But this has nothing to do with this, right? In my calling program, whether it's main or hashFind or whatever, this is the caller. I'm doing something like this, character first, bracket 1000, and then I say list find, and I give it a sentinel, and I give it a plate, and a first, and a last. When I come back from here, this is not going to have changed, because I'm not copying into the address given by this, I'm copying into the address given by malloc. It's a new block of memory. What I have done is, number one, I've created a memory leak, right? Because once I return, I have no access to this block that was malloc. And two, I'm not changing this variable. And the reason is the way that C passes things is strictly by value. When I call list find, I'm not passing this string. I'm passing the address of the first character of that string. And so if I just do this without allocating memory, it uses that address where this string begins and it starts copying into there. That's going to work great. But if I allocate space inside here, I'm going to be copying into a totally different location in memory. And when I come back, the thing that this was pointing to is unchanged. And if this was null to begin with and I try to do something with it, I'm going to segfault. The only way you could get around that would be if you did this as like a char star star first. And then I could do something like star first equals malloc, and then string copy into star first and all of this stuff. And that would work, but that's not a direction we want to go. But that's the only way that I could actually change the value of first, would be to pass its address to the list find function.
I think that makes sense. It's just still a little baffling that the argument, because when you have that statement where you set the argument address to that new one that you made, I would think that it would still know that address.
So you know, here's a function that I pass an integer to, and inside here I set that integer to 0. And in my main program, I say, you know, x equals 10, and I call my fun x. And when I come back, x is still going to be equal to 10. Right? Even though I set I, which was the name of the variable, to 0, that does not change the value of x up here. Right? Because C passes things by value. And it's the same thing that's happening here. I'm creating a new block of memory, so I'm making first point somewhere else, but the value of first is not changing.
Okay, yeah, it's more obvious with the integer, but
yeah.
I think now I'm seeing it better now.
Okay.
Thank you.
Yeah, you're welcome. It's a the whole call by value, call by reference thing is always challenging in programming languages. Some languages like Pascal, I think, will let you do either. C just passes by value, and so if we need to change something, we need to pass an address, or, you know, return our value as a function value, which is what we're going to do today. We're going to pass back information by using the return statement. All right, let's see. What else can I tell you about PA3? Saw some cases where people were using the wrong hash function. And if you use the wrong hash function, you're not going to get the correct results. Things aren't going to go in the places they're supposed to, and so on. So the hash function was specified. There were some challenges around coding this function, and in particular deciding on how to do the loop. And so the summation is written like this: sum from I equals 0, string length of plate minus 1. All right, the goal here is that, you know, if we have a string like HELLO, string length of that is going to be 5. String length tells you how many characters, not including the null terminator. So 1, 2, 3, 4, 5, string length will be 5. If you look at indices for these characters, the first character is index 0, the last character here would be 4. So this number up here, string length minus 1, that's the index of the last character in the string. Now when you do a summation, I equals 0 to some number, it means start with this number, go up to and including that number. Which makes sense because we want to include the last character. If we didn't do that, we'd be ignoring the last character of the license plate. And, you know, ABC123, ABC124, ABC125, they would all hash to the same place. It wouldn't be a very strong hash function. So we want to start from 0, go up to and including that number. So how do we do that as a for loop? For I equals 0. I is less than or equal to string length minus 1. This is good. The way that I usually code these is for I equals 0, I less than string length. That's also good. Since I is an integer, if I is less than string length, it's going to be at least string length minus 1. At most string length minus 1. So these two loops will iterate exactly the same number of times. If string length is 5, this says while I is less than or equal to 4. This says while I is less than 5. While less than 5, the largest values are going to be 4. So those are good. There's a pair of ways we can do this that are not so good. right? This is going to stop too soon. It's going to take I from 0 and go up to string length minus 2. But when we increment once more and we get to string length minus 1, I will no longer be less than string length minus 1. It'll exit our loop, and we won't take into account that last character. So that stops too soon. And this one is going to run too many times. Because when I is equal to string length, it's still going to loop once more, and we're actually going to iterate on character 5, which is the null terminator. For this assignment, that's not going to hurt us, because if that character is a null, if it's a 0, we're not going to end up adding anything to our hash value. But if we had a different formula on here, it's possible that using that last value could, have some ill effect. And so pick one of these that you like typing a lot, because you'll be typing it a lot the rest of your lives, right? And make sure you understand why it's the right thing, and then I would say stick with that. And yeah.
So the null terminator, when you're doing a for loop and you're doing it as an integer in this value here, so that's going to come back as a 0.
If I tried to access, for example, plate bracket 5, that would come back as a 0, yeah.
Okay, so if you're doing something where it multiplies the characters, that would really screw you, but adding it would...
But if I was doing, like, I plus this thing and adding that, then I'd be adding an extra term.
Oh, okay.
Yeah.
So no matter what, it will throw you off a little bit.
Yeah, sometimes a lot.
Okay.
Sometimes a little.
Gotcha. All right.
Plate bracket I, right? Plate is a string. It's an array of characters. So plate bracket I is the ith character. And if I just, if I have a string called plate, which contains HELLO followed by a null terminator, and I use plate bracket 0 in an arithmetic expression, it's going to use the ASCII code for that character. So it's gonna return a 72 in this case, I think. Because characters in C are integers, they're really short integers. They're 1 byte long, and so if I actually just put plate bracket I inside my for loop and I multiply by I plus 1 times I plus 1, it'll just multiply it as its ASCII value. And so initialize a sum to 0, add this value to it inside your for loop, and then either there or after your for loop, set your sum equal to some % hash table size. That gives you the hash value. All right, let's see, anything else in there? I guess the only other thing is hashFind. Right, so we want to search our hash table for a plate. Our hash table consists of, say, 100 linked lists. And we have a list find function that will search a linked list, but you really don't want to make a loop in here. For I equals 0 to 100, check each linked list to see if it contains the plate. Because that's really inefficient. That's checking the entire hash table. We're losing the fact that this is a hash table. This should be, something closer to order 1. What we'd really like to do is just search one linked list, the linked list that potentially contains a license plate. So if we iterate over every single linked list, we're losing our efficiency. So how do we know which linked list would contain our plate? Well, we find the right sentinel node inside the array of sentinel nodes. And how do we know which sentinel node? Use your hash function on the plate. That's what the hash function does. It says, hey, if this plate is stored in a linked list, it's in the linked list whose index is this. So take your plate, run it through the hash function that gives you an index into the hash table, look up that element in the hash table. This is the sentinel node of the list that could contain the plate. And now we can just call list find, pass it that sentinel node, the plate, and the first and the last. List find is supposed to check this list for that plate, and if it finds it, copy the first and last name from the node in the list into these variables. hashFind is supposed to do the same thing. Search the hash table for the plate, and if it finds it, copy the first and last name into these variables. Well, the copying business is being done by list find, and list find is going to return a 1 if it finds the plate. In which case, hashFind should return a 1. If list find does not find the plate, it will return a 0, in which case hashFind should return a 0. So we want hashFind to return whatever list find returns, so we could just say this, return list find. And there's a one-line hashFind function. And so this kind of thing, and this kind of thing, right? This is why we're talking so much about modularizing, about partitioning off who's going to do what. So that when I want to, search my hash table, all I have to do is just, punt to the list finder, take the value it returns, and just return that. And know that my list find is going to populate these variables as needed, so when I return, those variables will have the right values in them. And modularizing is what makes it possible to write, the kinds of programs that we write today. The things that, are gigabytes to download. It's because we don't constantly reinvent the wheel. We want to build a house. We don't have to smelt the iron to build a hammer, and then get out an anvil and start hammering, nails into shape so we can put our boards together. We just buy a hammer and an anvil, bunch of nails, and we use those. Thank you. Right, so same idea here. And 223, we're going to take this to an extreme, because we're going to have hash tables and linked lists and all kinds of things available to us in Java, and we're just going to use those and put them together and do all kinds of wonderful things with them.
Out of curiosity, what IDE do you recommend for Java?
Java, we're going to use Eclipse.
Eclipse, okay.
And Eclipse is probably nobody's favorite IDE, but it's pretty good at staying out of the way. And a lot of fancier IDEs really kind of get in your way. They force you to learn to speak their language. And I'm thinking about things like IntelliJ, which is fantastic if you're developing on the job and you want to be efficient and you want a uniform look and feel across the team. It's great. But when you're trying to learn Java and you have to, figure out how to appease your IDE, your integrated development environment, it's an extra challenge that I don't want people to deal with.
Yeah, I think once you open a project, have the build path already set up, it's pretty easy to test your programs too in Eclipse.
Mm-hmm.
I find Visual Studios, it's kind of rough sometimes. You open a command line or something like that.
Okay. Yeah, it's also open source, I believe. It's
Yeah, it is.
It's freely available and it's fairly stable. You can get older versions of it, and it works pretty predictably. I learned a lot of the stuff with NetBeans, and I love NetBeans because it was really small, it was very fast, it was a quick install and so on and so forth. I tried to go back to that for class a couple of years ago, and NetBeans just felt like it had gotten so bloated. It was trying to be what all these other interfaces are, and it felt kind of disastrous trying to use it to teach. So yeah, we're going to stick with Eclipse this year. But a lot of what we do in Java, we're going to do from the command line, and we won't actually start with Eclipse until partway through the course.
Okay. Neat.
All right, I think that's the main stuff that I saw on PA3. A few makefile issues, right? Make sure that your makefile makes sense. When you say make, it should compile everything that needs to be compiled, leave you an executable. If you say make again, it should say everything is up to date, and that didn't always happen. If you change a program and you want to recompile, you should just have to say make. You shouldn't have to say make clean or anything like that. Just make, right? And that'll figure out what to recompile. And when you're developing code, right, you don't have to type GCC, you don't have to, do wildcards. Just say make, M-A-K-E, enter. And it should, recompile the stuff that needs to be recompiled, give you a new executable. You run it, it doesn't work, edit your code, make, run your program again, try it. So it's a really rapid development cycle. And that's what we're after, right? We don't want to spend time fighting the tools. We don't want to spend time, chasing cursors with mice and things like that. You want to make a change, build your program, run it, see if it works. And it keeps you in that headspace of, you and the code being one, that kind of thing. Yeah, go ahead.
Can I ask just to make sure, because I've never had that issue before, but if I run into it, I'd like to know how to fix it. What would cause it to just keep recompiling if you say make and not saying it's up to date?
The main thing is, so when your make file, you have your first target, which is like plate, and it needs, plate.o and gcc-o plate.o, and then plate.o depends on plate.c and gcc-c plate.c. But if you mistakenly do this, then when you say make, it tries to make something called main, and it does that by linking plate.o to the runtime library and giving you a plate. If you say make again, it'll look in your directory, there's no main, it's going to do this again. And it was just, you copy the old make file into the new, but the main program has a different name, and so it does this. So just double check. Yeah, just a target issue.
Okay.
So double check, and always double check before you submit, right? Once you've got your tar file and you're ready to upload it, take a breath, copy your tar file to a new directory, untar it, say make, run some test cases, right? That will potentially save you a lot of points, because I'm still getting code from people where, they added their name at the last minute, but they put a single slash, and then put their name in. And if you try to compile something that has this in the beginning, you will get like, a zillion errors. Because the poor compiler is like, well, why are you trying to divide something by Nick Macias, And it's really easy to catch. Just, untar, make, and then execute your program, try a few tests. And in cases where people submitted code that would not compile, that, printed out a zillion errors, I'd spend a little bit of time and I'd go in and try to fix the errors. If it was something like this, I'll go in, I'll add another slash, I'll re-say make, everything works great, I'll go ahead and keep grading and take off some points. But university, a lot of your code is going to be auto-graded, and if the system tries to compile it and it gets a compile error, that's it, 0, right? And then you got to go chase down the grader and explain and hope that they'll take pity on you, So always do that double check.
Is that like your one-day projects from the last one, the ODPs?
Yeah, same idea, except some schools will do this for like, the main programming assignments, which can be nice because it lets you, know what your grade is going to be before you turn it in. You can have it auto-graded and get some feedback from that, but it's also harder to argue points that way sometimes.
Now, is that one of those, kind of the same thing where you can run it and grade it up until the deadline kind of thing for most people?
It depends on the course and the teacher, and some of this is anecdotal that I've heard from others.
Okay.
All right. Let's see. Any other questions, comments on PA3?
Are we ever gonna come back to this and do something maybe a little more efficient with it? Like, I thought maybe it would be cool if you could combine this hash program and say a binary search tree at the same time,
Mm-hmm.
and as a means of chaining. Are we ever going to come back to this problem in 224 or 223?
So there's other things we could do. PA4 is actually going to be like PA3, but with binary trees. And once we do that, that's probably, effectively as efficient as if we did a hash table with binary trees. But you'll see hash tables, probably on the final exam, but you'll also see them in other courses. After Clark, at a university level, you'll probably do programs with hash tables and so on. So if you did not, figure this out completely, I would still say, try to figure it out, try to get more comfortable with the ideas and so on. Partially for the final exam, because there could be a hash question on there, but also, for next year or whenever you transfer, it's something you're liable to encounter. But we're going to move on to binary trees, and we're going to basically code the same program, build a database of license plates, and then do lookups and such. But we're going to do it with binary search trees. And BSTs are going to be extremely efficient. They're not going to be order 1. But for 1,000 license plates, ballpark order 10. Which is, basically order 1. It's rarely going to take us more than say 20 operations to look up a license plate if we have 1,000 in our database. And if we're really good, if we balance our trees, it would take 10 operations, worst case. Alright, so I'm going to close the door on PA3 for now. But you can always ask questions. But let's go ahead and let's start looking at PA4. And so let me get into this a little bit, and then we'll take a break, and then we'll get into the gorier aspects of it. So PA4, very similar to PA3, building a database of license plates, but using trees, binary search trees, to store them. And so there's a sample program on the server. There's sample programs called Plate4 to differentiate it from Plate. It will ingest exactly the same kind of database file, so you can use database.txt to play with. And it starts the same way. Your executable is going to be called Plate, not Plate4, right? So Plate followed by the name of the database file. And it should open the file, ingest it, build a tree, and then process user commands. If it can't read the file, print out error and exit. It's the same as PA3.
So this one, I guess because we're using a tree, it's going to create its own leaves and everything, right? So we can't really specify
The size.
and whatnot.
Yeah, there's no need or opportunity to say, use 1,000 cells or something like that. So there's never another argument on here. It's just the name of the database, and we'll talk about how we build the tree step by step. And then it's keyed on the plate, same as before, right? And so the user can so you ingest the file, right? Same format. Build up the tree. And again, the nodes contain pointers to strings for plate first name and last name, so you have to allocate space, malloc, string length +1, all of that stuff. And then you ask the user what do they want to do. And mostly they'll type in a plate, hit enter, and it will either say, plate not found, or it will print out information about the plate. And then there's 2 commands that the user can use. The first is dump, which will display the contents of the tree in a variety of ways. But you can also delete a plate from the database. And so this is the new functionality beyond PA3. I can say delete followed by a plate, and it should remove that plate from the tree. And this is going to have to be done in a very specific way using a very specific algorithm. And what should I call this? I don't know how to make it more plain. Delete must follow the exact algorithm we're going to go over in class, right? There are different ways you can delete from a binary tree. You might code something that works perfectly, deletes the node, no problem, and lose points because you're using a different algorithm. So we're going to talk about exactly what the algorithm is. It's the only algorithm we're going to use in lecture, and that's the algorithm you're required to use in PA4. So delete will delete the plate if the plate's found. If it's not, it'll print out, plate not found. And then your only other option is Control D to exit the program. Control D, free the memory, say goodbye, and exit.
So a lot of this main program will follow the last.
Yes. So you can reuse a lot of PA3's main. We don't have a load command, we don't have dump followed by a number, and we have a new command, delete, followed by a plate. And we don't have to process, a numeric argument when we start the program. But other than that, it's basically the same wrapper. You initialize a tree instead of a hash. You open up a file, you ingest from here, you break it into 3 fields, and instead of calling hash add, you're going to call a tree add function to add these things to your tree. So when you ask for a plate, right, it should print out first name, colon, the name, new line, last name, colon, the name, right? So I want to see first name and last name on 2 separate lines with these tags in the front of them. And then the dump command is the oddball in all of this. So dump should print out 5 things. The first thing it should do is print out the tree height. So I want to see tree height colon followed by an integer, which is the height of the tree. And we're going to talk about how to find tree height a little bit later today. And then it should print out the word balanced followed by either yes or no to tell me is the tree balanced or not. We'll talk about tree balancing either today or Thursday, what it means to be balanced and how to test that. And then I want you to print out all the contents of the tree 3 different ways. The first one is in order, left node, right. And this should end up being alphabetical because when you do an in order traversal on a BST, the data comes out sorted. Then you're going to do a pre-order, node left right, and then a post-order, left right node.
And node is the root.
Node is the root, correct.
Okay.
All right. And I want the output exactly like this. I want the tree height followed by a number. I want balanced followed by yes or no. I want in order, pre-order, post-order. If the same information is there in a different order, I might take off points. Depends how many people are doing it. So stick to this order.
So one should be alphabetical from A to Z, one should be from Z to A, and then the other one's kind of going to be jumbled, right?
Actually, this one is alphabetical A to Z. These will kind of look jumbled.
Okay.
There's no obvious rhyme or reason to the order.
Okay.
All right. So let's sample code this, and then we'll do a break. So let me hop onto the server. So it's built up a database in memory. It's saved it as a binary search tree, and now it's asking me for a license plate. So if I type blah blah blah, plate not found. If I just hit an enter key, it's looking for an empty license plate. I don't happen to have one, so it should just say plate not found. If I put in a valid plate, it should give me the first name and the last name.
Or cheese.
So I can delete, let's delete more cheese, and it says success. And now if I look for that same plate again, it says plate not found. If I try to delete that plate again, it says plate not found. And then the dump command is going to spew out a bunch of output. And it's going to be hard to find anything in here. So if we scroll back up, we can see what the dump command printed out. It printed out tree height 21. So the distance from the root to the deepest node is 21 hops. and balanced it says no. And then I've got 3 traversal orders. Left node, right. This is in order. Plates are sorted alphabetically. AAM, AAP, AU, and so on. There's some B's and C's and so on. And at the end of all that should be, you know, the ones at the end of the alphabet. I can get there. I'm getting my scroll wheel exercise.
So, the last program when I would dump everything, I could only go back up to like cell 15, because after that it wouldn't let me scroll up any higher. Is there a way to get past that?
Yeah, were you using PuTTY?
No, I'm using the server with Xubuntu.
So you're running this on the Linux server, or are you running it on your local Linux system?
No, running it on the server.
Okay. How are you connecting to the server?
SSH.
SSH. Okay. So your terminal window has scroll back options, depending on what your terminal window is. So on this one, if I turn on my menu bar and I go to settings, and edit current profile, scrolling, so you can set how much scroll back you want. And most terminal programs have an option somewhere. Sorry, say again?
How did you open the menu bar?
So I normally have it suppressed, so if I just right click in this middle area, I can say show menu bar.
Oh, okay.
And then under here, under view, I can maybe under settings I can hide that. But then if you right click here, there's an option for show menu bar. But this is a terminal program called Console, Konsole. And there's different programs you can use. I like Console, but there's lots of different options. gedit is another one, and so on.
Yeah, it had a scroll back of 1,000.
So okay,
click
cool.
The unlimited scroll back.
Excellent.
Perfect. Thank you. That'll help.
All right. So the other thing. So there's my Control D to exit. And you know, if I go in here and maybe delete a plate and exit, I should come back. You know, all heap blocks were freed, no leaks possible. But one suggestion: make a smaller database to work with. So, you know, copy you know, maybe call this small.txt, and let's hop in here and just keep 5 lines. So now I can say plate 4 small.txt. And if I say star dump, I can see all the output. The tree height is 3. It's not balanced. There's my 3 traversal orders. And make a small database. Either hack up the one on the server or build your own database, you know, with names you can remember. And use that when you're developing. Don't force yourself to scroll back through 3,000 lines of text every time you want to know if your tree was balanced or not, right? Make life easier on yourself. All right, so let's do a 5-minute break, and let's come back at 2:14, and we'll keep going through this. All right, I'll be back in a few. Well, you got the apron.
Yeah. Well,
Excellent.
anytime that flour is involved, it's a good idea for me. So yeah, look at it and tell me, is that that was poopy me?
Yeah, go for it.
Okay.
I'll warn you, that may not be a great batch of dough.
Okay.
Normally it rises a lot more, so.
Well, good. Less pressure.
Yeah, that's pressure. So yeah, lots of flour on the board, and just try to stretch it.
Without pushing it.
Yeah, you want this on?
Yes. Oh.
Good thing is, it will come out fantastic. Alright, we're back. Alright, some more details of PA4. So this is how it runs. And you know, you're welcome and encouraged to use the sample program /temp/plate4. And you can give it any database you want, right? So if I do small.txt, right, and I give it plates like that, and I run it, then you know, my in-order traversal works. My post-order traversal will actually reverse alphabetize in that case, but the pre-order is kind of hit and miss. And you know, if I just sort of put these in like some arbitrary order and print these out, who knows what the order is. The only thing you're guaranteed is the in-order traversal should be in order. That's why it's called in order. And you should be able to confirm the behavior of your code using the dump command. So the dump command's not a bad one to build early on. But let's build this tree by hand using this database file. So we're ingesting from this file one line at a time, starting with the first line. And so EEE is definitely going to be the root, because our tree is empty to begin with. When you add one node, that node becomes the root. So the next plate we read is UUU. Where should that go relative to the root? Yeah, go ahead.
That's going to go to the right.
It's going to go to the right because U comes after E. So we're alphabetizing, and remember we alphabetize using string compare. So string compare takes two strings, tells us what the ordering is of them. And so UUU will come after EEE, so it goes to the right. And then we read our third plate, I, and where should that go?
That's going to go to the right and kick the other one down.
Right, so it's going to go to the right of EEE. And when we get to UUU and we look at I is smaller than U, so it should go to the left. And there's nothing currently to the left, so that's where we're going to put I. And as our tree grows, there's more spots available. We've got a spot here, and we've got two spots here. But to add a node on paper, so we're looking at O, we start at the root. O is bigger than E, so we go to the right. It's smaller than U, so we go to the left. It's bigger than I, so we go to the right. And there's nothing there, that's where the O goes. And then our last plate is A, and we start at the root. A is smaller than E, so we should go to the left. There's nothing there. And so that's where the A goes. Now the in-order traversal is going to be alphabetical A, E, I, O, U, which is what we got up here. The pre-order, though, says, hey, first let's visit the root node. That's the end part, so we're doing node left, right. So first we visit the root node, and then we visit all the stuff to the left, which is AAA, and then we visit all the stuff to the right. So how do we traverse this tree over here using node left, right? First we do the root node, and then we traverse everything to the left. And how do we traverse this tree using node left, right? First we do the root node, and then everything to the left, which is nothing, and then everything to the right. And so now for this node, we've done the root node, the left, and now we do the right, which is nothing. And now from the original root, we've done the root node, the left, and the right, and we're done. And this should produce EEE, AAA, U, I, and O. Right? And that's what we got here, EAUIO. The post order, which is left-right node, will say, hey, let's look at the stuff on the left first. So that's an AAA. And then traverse all the stuff to the right. And the last thing is going to be the root node, so that's going to come out at the bottom. So how do we traverse this post order left-right node? Well, first traverse the stuff on the left. How do we do that? First traverse the stuff on the left, which is empty, then the stuff on the right, which is O, and then the root node, which is I. That's the left subtree of this. Traverse the right subtree, which is empty, and then traverse the root, which is U. So A, O, I, U, E, that's the post-order traversal. So this can also help you with practicing traversal orders. Now, we don't normally have to do this by hand, but it's nice to be able to do, and you might see test questions on it, right? So it's nice to practice traversing trees by hand, and you can use this program, Plate 4, or the program you develop, to see what the different traversal orders are.
I used Microsoft Paint all over the place.
Yeah. And then the tree height, finally, it says tree height is 3. Remember, height is the depth of the deepest node. And the depth of a node is the number of steps from the root to the node. So here's our root. This looks like our deepest node. How many steps? 1, 2, 3 steps. This has a depth of 3. The tree has a height of 3. So that's why it's reporting 3. And it's not balanced. Roughly speaking, we got too much stuff on the right, not a lot of stuff on the left. But we'll do a formal definition of balanced probably on Thursday. And it'll be another recursive algorithm. It's like 4 lines of code. It's not a big deal once we understand it. All right. So that's the behavior of the program, and that's our sort of verification by hand that it's doing something like the right thing, at least for this particular tree.
So, for the height, are we going to do something like check the left and then check the right and then compare the two, which one's bigger, kind of a deal?
Basically, yeah.
So like a recursive function to do that?
Yep, exactly. Yeah, it's gonna be very close to that.
Okay.
My document camera died, so I gotta bring
Is
that
that kind
back.
of, I'm curious, like, I guess, and we'll go into it, but if you just check the left and then check the right, you're not really traversing the whole tree, you're just kind of going left and going right, right? You're not really doing the whole thing. Well, I guess if you're using recursive functions, it's a little different. So.
Yeah, so you're not doing the whole tree, but the recursive function is.
Yeah, I guess I gotta remember that.
Which is pretty glorious. Yeah, so I think we'll get to tree heights today, and that'll be a nice illustration of it.
This would be like a pathfinding algorithm to actually find the height, right?
Yeah. But a pretty painless one, relatively speaking. All right. So that's the behavior of the program. Yeah, go ahead.
Yeah, I think.
Oh, I'm still here.
I think he froze.
All right.
Oh, is he back? Yeah, he's back.
We lost you there for about a minute.
Oh no. Okay, I just got a notice saying that my internet connection is unstable. So I don't know what that's about, but hopefully I didn't say anything important. I'll throw a tag on the video saying audio dropout. Go back and just listen like a minute before that, because the audio should be in the recording, and double check that you got everything. All right, but you can hear me now, correct?
Yes.
Okay, cool.
Yep.
Are there any BST functions that involve iteration? Yes, so we'll talk about other ways to traverse a tree that work well iteratively and actually don't work well with recursion. But they won't be part of PA4. But we'll play around with some of those. All right, so let's talk about implementation. So your node structure looks like this. Your node consists of basically a set of data fields, plate first last, same as PA3, and then a left child and a right child pointer. And those are pointers to struct nodes, which is what this whole structure is. And then I'm type defing what I call an uppercase node to be a pointer to a struct node. So it lets me, when I want to talk about a node, just declare it to be an object of type, uppercase node, and I don't have to worry about the word struct, and I don't have to worry about putting in the asterisk. And so most of the time, I'll just use a node when I'm referring to nodes in the tree, when I'm declaring variables and so on. The only thing is when I'm mallocating space, I want to actually use a struct node instead of a pointer to it. And so in our program, we're going to have a root to our tree declared in our main program, and we initialize it with null. Right, so we start off by saying root equals null. We define it as a type node, and then ingest the database, build the tree, take in user commands, process it. So details. So you need at least these functions. There's a height function, takes the root of a tree, returns the integer height, and we'll talk about that next. There's a balanced function, takes the root of a tree, returns a 1 or a 0, telling me the tree is balanced or not balanced. And we'll go through that next class probably. So there's an add function to add to a tree whose root is given here, and we basically pass that the plate first name and last name. It should make a new node, put it into the right spot in the tree, and the add function returns a pointer to a root node. And so this is the code that we built up last week where we said, root equals add, root equals add, root equals add. So every time we call add, we're going to set root equal to the result of that. And it'll just keep, glomming new nodes in.
Just real quick so I can hopefully start working on this. That one is going to basically use the license plate, check that data, and then add accordingly, correct?
Mm-hmm. Right, so plate is the key. That's the thing that we compare to the root, and that tells us whether to move left or right. And then first and add are just data fields that get copied into the node.
Okay. So it'll check the plate. If it's bigger, make it to the left. If it's smaller, make it to the, or excuse me, other way around.
Yeah, other way around. Yep, you got it.
Yeah. Okay.
Okay, cool. All right, and then search takes a root of the tree, a plate, first and last, and just like with the hash program, if it doesn't find it, it just returns a 0. If it does find it, it returns a 1, and it copies from the node in the tree into these two string fields. So when we come back from search, if it gives us a 1, we know not only that the plate is in the database, but we know the first and last name associated with it because it's been copied into these arguments. All right, and then delete will take the root of a plate, the root of a tree, and a license plate, and it will delete that from the tree. And this also returns a root, just like the add function does. We're not going to talk about delete until probably next week, because the delete algorithm is a little trickier. But it can be the last thing you do in PA4. All right, 3 traversal algorithms: in order, pre-order, and post-order. And then treefree that we talked about in the very beginning of class that takes the root of a tree and frees all the memory associated with it. If you get your add to work, that's awesome. You can always slim things down, but leave it in the form that makes sense, I would say. Code that works and makes sense to you, that's the best possible code. If you can make it slimmer, if you can make it faster, if you can make it fancier, that's different, right? But particularly for a class, I like code that works and is understandable to the person who wrote it. And then you can go on from there if you want to, slim it down or something. All right, here's my obligatory suggestions. And these may help you, they may not. I'm putting them out there because I think they will help you, but you may not follow all of these. But here's some ideas for how to attack this, because this is a big assignment, right? You can reuse part of the main program from PA3, but these functions can be tricky to get right. when you get them right, they won't be that big other than delete. Delete's going to be fairly sizable. But these functions and height and balance, if you write them a certain way, they're going to be pretty small. But it's getting them just right that is going to take time. These traversal functions are like 4 lines each. The treefree is like 4 lines. But it's a lot of work. And so some suggestions on how to approach this, right? My first suggestion, make a tree by hand, right? We did this in some sample code last week. We just, made a new node function. We created a root, set it to new node. And then we said root arrow left equals new node something, root arrow right equals new node something. We kind of built up a tree like that. And we did that with integers. You can do this with integers, right? And when you're trying to better understand how trees work, start with a tree of integers. Forget about strings and string copy and all that. Just use plain old ints. Right, and that means you can mimic some of the code we've been doing in class last week, some of the sample code on the server, right? And so cobble a tree together and work on your traversal, right? So go back and review the notes, maybe look at the code, but try to write this yourself in a way that makes sense to you. And once you've got, the in-order traversal working, go ahead at that point maybe and do the pre-order and post-order. And make sure they work, and you can build a database of integers. So these are license plate, but I could make this 30 and 20 and 50 and 10 and 40. And even though they're strings, if I only have one digit that's changing, right, these should alphabetize the same way as numeric order. It doesn't always work, but if I use 2-digit strings, it should work fine. So I can see, how my tree should be built in these different traversal orders, and you can test your code like that. Right, so cobble a tree together, by inserting this data by hand and figuring out how to place those nodes, and then get your traversals working. And then work on your search function. And again, you can do this with integers, right? Just take an integer and search for it by searching the left and right subtree. And that's, another nice recursive function. And then maybe go ahead and switch over to using strings. Right, instead of just integers, or not, you could develop more stuff with integers, but start moving towards, working with a node structure from PA3 where we have, 3 strings, a plate, which is the key, and a first name and last name, and try to do your search function, and, don't worry about fancy parsing, don't worry about all this stuff, right? If I have a search function that I think should work, I can drive it like this. Search for root, sumplate, first, last. First and last I've declared to be character arrays. Save the result. If the result is 1, I'm going to print out the word found, and I'll print out what the first and last name are. Otherwise, I'll say not found. Now call search again with a different plate, and see if it finds that and gives you the proper first name and last name. And then maybe call it with a plate that's not in your tree, and see if it comes back and says not found. And I'm not spending time working on my main program here, right? I'm working on the tree functions. That's the new piece for this assignment. And I'm testing it with different main programs as I go, just by calling functions. By the time you finish the main program that you're going to turn in for PA4, you may have written, 20 or 30 other main programs to test pieces of your code and then thrown those away. Or, left them. Don't throw them away. That's good. That gets you better at writing programs and compiling and testing and all that kind of stuff. So don't make things harder by trying to get your whole main program working with parsing and all that stuff while you're trying to develop these pieces, right? Work on these pieces first. Definitely draw lots of pictures on paper, right? Lists are fairly complex. Trees are significantly more complex because not only do we have two children on each node, but it, bifurcates, and the deeper the tree is, the more things are branching out. And trying to do that in your head can be pretty rough. So get good at drawing pictures. All right. And a side note here, right? Make friends with VI. If you're not already comfortable with VI, this is a really good excuse to dig deeper into that editor. So for example, if you're sitting on a cursor, you can take 4Y, uppercase Y, not in insert mode, because that'll just insert 4Y, but in command mode, 4Y will copy 4 lines of code starting with your current line. And then if you move somewhere else and hit a P, it will paste those lines into your file at that point. It's a lot quicker than using your mouse to highlight and going to the menu and saying copy and going to the menu and saying paste, right? So start playing around a little more with VI, right? W and B will let you move forward or backward one line at a time, one word at a time, and don't shy away from writing test code because you don't want to get into the editor and do all that typing, right? You can do a lot of this pretty easily if you're comfortable with VI and if you know a few of the command line commands that you can use. So you can take this as an opportunity perhaps to dig deeper into that. So that's a side note. All right, move on to your add function. And again, you don't need to be parsing your database file. You don't need fopen and all this kind of stuff. Just call add a few times. Add, give it the root node, a plate, and a first name and a last name. And do that, maybe 5 times with different plates and names, and then call your traverse function and see if it prints out the data in sorted order. And then maybe, do some of your search calls. And so you can get all this working from, test programs. And that's a big key to efficient programming, is being able to test your code along the way. And so by the time you get to reading in your database file, you should be pretty confident that your tree functions work, right? Other than delete. We're leaving delete for the end. But adding to the tree, searching the tree, printing the tree, you should have that nailed down, right? All right, so now abandon the tree that you built by hand and start with a tree that's equal to null. And see if doing this creates a tree with one node. And then calling add again and again, see if that adds to your tree, or if it segfaults, right? And you want to be doing one new thing each test. Don't try to add 5 features to your program and then test it, because if something blows up, you don't know where it's blowing up. It's one of the 5 new things I added. If I do the entire, 7 pages of PA4 and then I test my program and it segfaults, thanks, I don't know what of the 7 pages of stuff that I just added is causing the problem. So do this in pieces. All right, so try adding to a null tree. If that works, now you can read in the database file. So you can probably mimic the code you did for PA3. Open up, the file with fopen. Parse the arguments, make sure there's a file there. Call fopen, make sure it's not null, complain if it is. Do a loop, do fgets, do an scanf to break it into 3 fields. But now, instead of calling #add, you just call add. Give it the plate, first name, last name, and this root that you keep building, set it equal to root. When you get to the end of the file, close the file, you should be done. Your whole tree should be ingested. What do you do at that point? I don't know. Call your left node right function and print it out. And do this with a small database file with 10 names. See if it's got all 10 names. So at this point, you're probably, most of the way done with PA4, other than delete. So you have to code height and balance, and we'll talk about those next. And when we talk about height, just a heads up, I'm going to talk about taking the maximum of 2 things. There is no max function in C. And don't get lost trying to find a max function. If you want the maximum of A and B, just use an if statement. Right? If A is bigger than B, A is the maximum. Otherwise, you can use B as the maximum. If they're equal, you'll end up using B. Doesn't matter because it's the same as A. So when I write pseudocode and I say, take the largest of these two things, don't get lost trying to like figure out, how do I compile and link in this library that I downloaded from GitLab that has a max function built in and all that. It's just an if statement, right? So we're going to do height next, and we'll see how this comes up. But keep in mind, right? This is the world you're creating. This program, it's you get to call the rules, right? It's got to do certain things specified in here, but how you do that is basically up to you. And don't be afraid to do things kind of the barehanded way, right? If you've got two numbers and you want to know which one's bigger, write an if statement. That's all you need. All right. After all that, I would say go ahead and work on your main program. Get that done. It's going to be close to PA3, but there's a few differences. Maybe leave, an empty thing for the delete command. And then go ahead and work on the delete function. Delete is a separate task. It can break a lot of things. It can plant landmines that will blow up later. You really want to know everything else is working perfectly before you code up delete. All right, and then as usual, start early, ask questions if you're getting stuck, or if you're not sure how to get beyond some point, or if you're not sure how to start, right? We can do a lot more, Thursday morning in office hours than we can, a week from Thursday in office hours when I've got 10 students and no time left, right? So start early and ask questions, and have fun. It's a cool program once you get it working. And once you've done some work with trees, you're in really good shape for most other data structures that we're going to deal with. All right, so upload your file as pa4.tar to Canvas by the deadline. I would like that tar file to contain all of the source code, including any .h files you have, and your make file. And your make file should include a clean option and should only compile things that need to be compiled. And so if you make twice in a row, it should say everything's up to date. If you change one file, it should recompile just the things that are affected by that change and build an executable. All right, grading. So I'm listing deductions for different things. These deductions, if you lost points on all of these, it's more than 100 points. You won't get a negative score, okay? If you don't submit anything, you don't get 100. You lose 100 points. Any makefile issues, 10 points. If I can't compile your program, you lose 40 points minimum. If I can fix it easily, I'll fix the problems and continue grading your program. If I can't, fix the problems, you're going to lose more points. Any warnings from the compiler, 10 points. If it cannot ingest the database file, that's 50. If it does something unexpected, if I try to use a database file that doesn't exist, that's 10 points. Unexpected meaning seg faulting or, reading in random data or something like that. If you don't put a command line argument, it should say, you need a command line argument, which is a database file or something like that. If it seg faults or runs with something random, that's 10 points. If license plate lookups don't work, ooh, thank you. Okay. If database license plate lookups don't work, that's 30, because that's sort of the main action. If you're not building the search tree correctly, that's 30. If you're using fixed size arrays for the strings instead of dynamically allocating, that's 15 points. The delete command is 15 points. If you can't get delete to work, just comment it out and put a note saying, I've got a lot of code for delete, but I couldn't get it to work. If trying to delete something causes a seg fault, you're going to lose seg fault points. Right? So don't jeopardize the rest of your program for one piece. And, worst case, it's 15 points. If you don't use the delete algorithm we're going over in class, you're going to lose 10 points, even if it deletes perfectly. Right? So that's that warning that I posted earlier. Dump command is worth 60 points. If you don't have a dump command, it's really hard for me to grade your program, because that's the main way I'm going to look at your tree. So that's a whopper, right? You got to have a dump command. Height not working or balance not working, 10 points each. Any of the traversal orders that are wrong, 10 points each. Valgrind issues or warnings or memory leaks, 15. So we're upping the bar on memory management. Control D should exit. That's 10 points. Yeah, go ahead.
So, I heard in the Discord yesterday, but I don't know if this is true. But for members of the A class, I thought we were going to, like, we didn't have to do balancing, but do we have to do balancing?
No, there's no balancing in this one.
So, what would the balance error be?
Where's the balance error? Oh, testing whether or not the tree is balanced.
Okay.
Right, so that's just running an algorithm that says, is it balanced or not?
So, we're not going out of our way to make the tree balanced?
No, in fact, you do not want to balance the tree, because if you do,
Oh.
you'll get different results from what I'm expecting.
Okay.
But there is a function called balanced, which tells you whether the tree is balanced or not.
By the way, small side note, how come for some of these Boolean functions we just use an integer instead of like a bool?
Because bool's not really a part of C.
Okay.
It's an integer at the CPU level, but there's like a standard bool that got added for C99, I think. But they're really just integers, and we're kind of staying, closer to the CPU level when we're working in C. That's part of why we're doing C right now instead of Python or something. So ints will work.
Is the whole philosophy behind even introducing bools in the first place just to save space? They take up less space than an integer?
They might be a character, but they're not bits, right? C doesn't actually like break things down to the bit level. But you could use a character if you wanted. But having a separate type kind of feels better in some cases, because we really want a Boolean. We want a yes or a no, and so making it a bool lets us sort of like have that mindset. But it's not like Java where Boolean is an actual type and it has a value of true or false. It's just kind of a fake.
Oh, that makes sense.
Cool. Dump is 60 points if it's not implemented. If there's a problem with your dump command, that's not 60 points off. But I want to make sure that you have a dump command that will call your tree traversals, your balance function, and your height function, right? And if the balance function gives the wrong answer, that's not 60 points off. It's 10 points because of a balance error. But I want to make sure you include that function, so I'm making that a bunch of points. Otherwise, I got to go in and I got to like change your main program and add, my own calls to your functions and stuff. Control D should exit. Main program should either process a delete command, a dump command, end a file, or do a plate lookup. Right? Anything other than these should be a plate lookup, including an empty line. That should be a plate lookup, which is going to say plate not found. Format issues on the output, 10 points. So you can try to get close to my output from the sample program. And if you're very close, if you uppercase plate instead of lowercase it or something, that's okay. But if you manage to match the output of the sample program exactly, you can capture the output by redirecting it, and then you can use the difference command. And difference will compare two files character for character and tell you if they're the same or if they're different and what the differences are. And that's kind of an acid test to make sure you've got all of the formatting details that need to be there. Well, I'm having some amazing homemade pizza right now.
Lucky.
Check that out. Whoa.
Now what pizza?
Yeah, totally.
Cheese, huh?
This is like fresh out of the oven. And it was dough 3 hours ago. All right. Questions?
I'm still not quite sure why we're not using bools. I guess it's just the fact that they're
You
smaller,
can
maybe?
you can take it as an arbitrary decision if you want. You know, same reason I'm calling the add function add instead of tree add. No particular reason.
That segues right into my question.
Okay.
Can we go over pseudo for add, like the kind of steps to look at when implementing that function?
Absolutely. So
obviously you're going to want to traverse the tree first, right, and find where it goes before you malloc memory and add stuff.
Well, yes and no. So how do we add to a binary search tree? If we're doing this by paper, and we say, you know, add 35. Well, on paper, what do? We start at the root. 35 is bigger, we go to the right. 35 is smaller, we go to the left. 35 is bigger, we go to the right. There's nothing on the right. We're going to go ahead and put a new node here, and that's where our 35 is going to go. So that's a recursive add function, a iterative add function, right? That's not recursive. That's just looping through and moving till we get to the right spot, and then adding our new node there. But we can rethink this recursively. Let's just say we're going to add, you know, data to the root. So I'm going to go back to my integer tree example, so we don't get caught up in string compare and such. And so if root is null, just return a new node. Make a new node containing data and just return that as the root. So if our tree is totally empty and we want to add a node containing data to it, make a new node, make that the root of the tree. Otherwise, we've got two possibilities. We've got a root, right? And so we look at our data, and if our data is smaller than the root, we want to add it to this left subtree. And if our data, like 35, is bigger than the root, we want to add it to the right subtree. And so we need two statements here. If data is less than the root data, then set root left equal to the tree we get when we add to the root left our data. Else our data is bigger than the root, and so set root right equal to the tree we get when we add to the right subtree our data. And then either way, return the root. That's the whole add function. Go ahead.
Oh, I'm sorry, I muted my mic as I started. So in this case, you're going to want to malloc everything and then check whether things are bigger and smaller, and then just, because you're always going to add, right? No matter what, you're adding a node when you call it.
But the only time I malloc is up here when my root was empty. If my root's empty, I need to create a new node. Otherwise, I'm going to let this function do the malloc and figure out where to put the node in and actually put the node in. So I really...
So you want to do, if root is null, then malloc, a new node, and then otherwise do the if-else statement, and it'll just call that recursively until it's null. Okay.
Yep.
That makes more sense.
Cool.
I was going to say, otherwise, every time you run through it, it's just going to keep mallocing more and more memory. And then you're going to have a problem.
Definitely.
Okay. That makes sense.
And what's actually happening here is that, you know, each time that we make a call to add, we're moving down the tree. So the first time we call add, we're adding to this entire tree. And let's say we're adding 35, right? 35 is bigger than root, so we're going to make a recursive call to add 35 to this tree. And when we come back, we're going to set the root to point to that new tree. And to add 35 to this tree, we're going to say 35 is less than the root 40. So let's add 35 to this tree. This is not here. And then let's set this root node's left child to be the result of that add. And when we say add 35 to this tree, we're calling a tree. We're calling it on a tree that looks just like this. A single node. And we're saying let's add 35 to that. And this is going to say, okay, 35 is bigger than the root node's data, so let's call the add function on 30's right child, which is null, and let's add a 35 to a null tree. And when we add 35 to a null tree, we're going to create a new node containing 35 and return that. And this function is going to say root right should be equal to the result of that call. This is going to set root right to be a 35. And then when we return from that call, the call up here is going to say set this node's left child to be the return of adding 35 to that. That's going to make the left child of 40 this thing. And it's going to kind of like leapfrog up all the way until we get back to our original call, when we'll have our original tree with a 35 added.
So I know we don't really have to worry too much about this in this process here, but if you compare the two strings together and it's equal to each other, like a duplicate, would that just be an additional statement in the if and else, and then just be return or?
So this is gonna break pretty horribly if we have duplicates.
Okay.
Because if I tried to insert another 40, right, I could put it to the left and to the right, or I could put it to the right and to the left, right? And it's gonna make things really wacky. It's gonna make search really hard and so on. So we're not gonna insert duplicates. And I don't think there's anything in here that requires you to deal with possible duplicates. And we're going to assume the database file we're reading does not contain duplicates. But you know, if you wanted, you could do something in here to search and see if the node's already in the tree, and if it is, just, you know, don't do anything. Just return the tree unchanged. But I'm not going to test that case. We're going to assume the database has no dupes, and you're not required to deal with that eventuality.
So for the string compare, then we should check if it's greater than or less than 0, basically.
Yeah, basically, if it's less than 0, go left. Otherwise, go right.
Okay.
I guess I did mine just right then.
Cool.
Because that's what I was like, maybe I could slim this up a little further.
Okay,
also,
cool.
This kind of explains why I think I had tree free a little wrong.
Oh, okay.
Where I was using like temporary variables and calling the function on those.
Mm-hmm.
rather than using the actual data, I made copies, I think.
Okay. Cool.
That's my best guess, anyway.
Sounds plausible. All right, let's talk about tree height. And so you know, this is part of a way to address the question why we're doing recursion, right? This is a very simple add function. It's really, you know, 3 statements. It's an if else, and it's a return. And if we didn't do this, you know, we'd need to have a current node and move to the left or the right. And when we get to a current node and, you know, we want to move to the right and current becomes null, we need to back up 1 step and then make our new node and stick it on the right of that. And we can do that, you know, it's not horrifying, but it takes some work. And traversal, when we want to print our tree, we'll do that next time probably. We'll show how to iterate and print out the contents of a tree without doing recursion, and that's going to be a fair amount of work. And tree height would be similar. So remember our definition of tree height. It's the depth of the deepest node. And so the depth of a node is the number of hops from the root to the node, and it looks like this is the deepest. And from the root we have to go 1, 2, 3, 4, 5, 6. And so the height of the tree is going to be 6 in this case. And you know, if I have other nodes over here, well, these nodes are a little deeper, but the depth of those nodes is 1, 2, 3, 4. And this is a depth of 5, and this is a depth of 4, and so on. So the deepest node is still going to be 6. And so the height of the entire tree is going to be 6. But there's a different way that we can think about height. Right, this we would need to visit every node, and then, yeah, maybe use some kind of static variable to keep track of the deepest node we found. But there's a different way to think about this. Suppose I look at my original tree, and I notice that, you know, there's a left subtree, and there's a right subtree. One of these contains a deepest node. In this case, it's this one over here. Well, in this subtree, what's the depth of that deepest node? It's only going to be 5. Starting from the root, it's 1, 2, 3, 4, 5. And so this subtree on the right has a height of 5. The subtree on the left, the deepest node is 1, 2, 3 hops. This subtree has a height of 3. So what happens if I move from the subtree to the original tree? The depth of every node in here increases by 1. Because however many hops it takes to get from here to a node, to get from the actual root, takes one more hop. I take one step here, and then it's however many hops it takes from there. So the depth of each node in here is 1 less than the depth of this node in the original tree. And the same thing on the left. The depth of each node in here, in this circled area, is 1 less than the depth of that node in the original tree. And the height is the depth of the deepest node. So if the deepest node is on the right side, the height of this entire tree is 1 less than the height of the original tree. And if the deepest node is on the left, the height of this left subtree is 1 less than the height of the original tree. And so I can define a height function by using that observation and doing the following. I can say left equals the height of the left subtree, and I can set right equal to the height of the right subtree. Whichever one of these is bigger, that's the side that has the deepest node, which is the side that should determine the height of the entire tree. So I'm going to say if left is bigger than right, let's return 1 plus the height of the left subtree, which is just left plus 1. Otherwise, and I don't need to say else because I'll return right here, so otherwise, return 1 plus the height of the right subtree. And there's our height function. Almost. So this is not built on the idea of starting from here, moving in every possible direction, keeping track of the deepest node. This is built on an observation that the height of this tree is exactly 1 more than the height of either the right subtree or the left subtree. And which subtree do I care about? The one that's got the highest height. If they're both the same, doesn't matter. It's the same height. I can use either one. So if the left subtree has a greater height, the height of the whole tree is 1 plus that height. Otherwise, it's 1 plus the height of the right subtree.
I'm a little confused about something.
Okay.
This is just under the presumption that it's only ever going to be one higher than the other?
No. I could have a tree that looks like this. And the height of this left subtree, distance from the root to the deepest node, is 2. And the height of this subtree, distance from the height to the deepest node, is 0. The left subtree has a greater height. If I do 2 plus 1 is 3. That's the height of this original tree. The distance from the root to the deepest node is 1, 2, 3 hops. We're adding 1 because when we move from a subtree of the root to the root, we add 1 hop. So however many hops it takes to get from this root to the deepest node, it's going to take 1 more from this root, right? That node right there, that link. And this is classic recursion. This is the rabbit hole that we'll lose ourselves in sometimes. And for a small tree, it's a useful exercise to sort of draw a tree and try to run through this algorithm on paper. And you need lots of paper so you can keep track of where you are. But it's an enlightening exercise. It's something we normally do in the classroom. I hand out papers that show you the call frames, and we work in groups, and we actually go through the whole recursive process. It's hard to do online, but we'll try to do that. I'll try to do that and let you see it, but it's more fun to do it yourself and more enlightening.
So search then is going to be very similar to add, right? Because you're just basically going to be recursively calling search.
Yeah, search, you basically just say...
If the plate is bigger than the root plate, go right, or go right, and then if it's smaller, go left, and then keep calling search.
Yeah, and you only have to call it once, right? You basically say if it's smaller, just call search on the left and return whatever that gives me. If it's bigger, call search on the right and return what that gives me. And so that's like another 4-line function.
And then you'll just have that if, right? Or if null, just return 0 or whatever.
Yep.
Okay.
And so yeah, we need one more statement up here, because the way it's written, to find the height of this tree, we're going to need the height of this tree, and to find the height of that, we're going to need the height of this, and to find the height of that, we're going to need the height of this single node tree, and to find the height of that, we're going to need to find the height of its left child, which is null. And so we're inevitably going to call height on a null tree, and if root is null, root arrow left will segfault. But if the tree is empty, if root is null, we don't need to do anything fancy to find the height. So if root is null, we just return the height of a null tree. And the peculiar thing here, right, a null tree has a height of -1. So empty trees have a height of -1. And why is that? Because it makes this work. Because here's a tree with 2 nodes and the height is 1. Right? Deepest node has a depth of 1, it's 1 hop from the root. Here's a tree containing just a root. The deepest node, the root, has a distance of 0 from the root. This is a height of 0. So an empty tree, which contains no nodes, if we gave it a height of 0, it wouldn't really work. We'd say it has the same height as this, but that doesn't make sense. So we define an empty tree to have a height of -1. And we define that because it makes things like this work. So that's a definition of height for an empty tree, and that becomes the base case for our height function. So there's how you calculate the height of a binary tree using recursion. If the root's null, return -1. Otherwise, find the height of the left and the right. Add one more than the greatest of those and return that. All right, so we are just about out of time. So Thursday we will revisit height and talk about why height is an interesting characteristic of a tree. And that will take us into a discussion of balance. And so we'll talk about what it means for a tree to be balanced, and we'll look at an algorithm for determining whether a tree is balanced or not. And then I want to go back and look at some traversal algorithms. I want to look at traversing a tree without using recursion, using a stack, and then we'll play around with using a queue, and then we'll move on to deletion, and eventually next week we'll talk about how to balance binary trees, which is not part of the assignment, but is a good thing to know. So lots of good stuff coming up. We'll continue talking about trees for at least the next couple of classes. You know, we'll keep talking about PA4 as questions come up and so on and so forth. All right, that's all I got for today. I am off to a meeting. Hope everybody has a great afternoon, and I will see people next time.
Thank you.
All right, thanks.
See you later.